Hi, everybody. I was uh, just looking around for some brushless DC motor animations, and I think I found a nice one here. Um, this one shows you what happens when you have a commutator, which is the part that rotates. So, welcome to another exciting microelectronics, microprocessor lecture. We've got an interesting set of technologies for us to review today. First, I'd like to ask if anybody had any troubles with the midterm. I know it was due last Thursday. Any questions about the midterm? Any questions? In our last exciting microcontrollers class, we were looking at a homework that involved some stepper motors. And of course, we had a nice lab about the stepper motors. And one of the things that was interesting about the stepper motors is they were brushless. And so when we think about brushed motors, we think about something where we're trying to get energy into these coils that are rotating. And as they rotate, they change direction and cause the motor to impart a spin. And because the requirement is that the electromagnetic field change direction, we need to energize the magnetic field differently. And to do that, we need to get energy into the part that rotates. To do that without getting the wires all sort of tangled up, we use this thing called a commutator and a brush. And the brush, you can see it over in here, is actually making contact intermittently with the various commutators. These are basically copper going around in a circle. And you might find this as a common motor design dating back to, dating back to the late 1700s with Michael Faraday coming up with an electric motor that he showed to the Royal Society. This was a great design if you wanted an electromechanical motor. But in the 70s, what happened was people figured out that they could create electronic motor controllers. And so they came up with this idea that you didn't need these brushes, which wore down occasionally and caused, perhaps a fixed rate of turn that was inherent to the motor. So what they did was they came up with these brushless DC motors, and we can find them in drones. And so here's it's kind of like, I don't know, we'll call it the motor taxonomy: brush DC motor, brushless DC motors, which is the ones we care about, stepper motors, which are really a kind of brushless DC motor. And here we go. This is there. Now we've got the permanent magnets on the rotor, and we've got the actual coils on the stator. And now we don't need any brushes, but we do need to know the position of the rotor as it turns around. And in order for us to do that, we get two choices. Either we get some sort of magnetically sensitized transistor that can tell us what the orientation is of the magnet as it goes by. That's called a Hall effect transistor. Or we can use the so-called back EMF that we would get from a coil if it has just been passed by a magnet and it's starting to turn into a generator instead of a magnet. So this is one of those things where, you know, you got your choices for design. The electronic speed controllers, or ESCs, that you buy are often miniaturized for things like drone applications. So when you go to the high efficiency brushless DC motors, which are in a great way just like our stepper motors we've been using, you need a controller. Now, of course, we built the electronic speed controller with our Arduino, but if you wanted to just buy one and hook it to your drone motor, you sure can. And they're not terribly expensive. I was just looking them up. In fact, I was shopping for BLDC motors, which are brushless DC motors. And in a way, that's just like what we were using with our stepper motors. So that's kind of neat, only we were building our own electronic speed control. So not to put too fine a point on it, if you went to Amazon and you wanted to find a brushless DC motor you could, and gosh, this is a nice big one, isn't it? Gosh, we don't want to buy $100 motors, but you can buy small ones. Here's a little one. And so there's, yeah, this is the kind of thing you might use, known as the outrunner. Here the outside would turn, and the inside is your stator. And so this is good for, I don't know, he says, multi-coptors, which I assume means more than one rotary wing. And look at the voltage these things take. Wow. So they're really pumping up the voltage and getting these things to spin at high speeds. And of course, you need special controllers, electronic speed controllers for them, because they are brushless. Anytime you run into a brushless motor, you're going to have to deal with the fact that you need an electronic speed controller for it, or you have to create one yourself. Here's a sensorless one. Now, when I say sensorless, it means it runs off the back EMF. That's pretty inexpensive. And I don't know if that'll work with the little motor controllers we just saw here. They'll probably tell you what you need when you go to buy it. They'll cross market to you and say, did you forget your controllers? And here's one that comes with a controller, so that's kind of convenient. And for people who are into this sort of high energy type output system, like you would find in a rotary wing aircraft, these are the ideal motors. They're very compact, very light, very efficient, and you can control them with great precision. Here's a controller, BLDC driver module. So this is just the sort of thing you would need in order to be able to drive your brushless DC motor. And apparently you got your choices. This one's for racing cars off-road. I assume this is not a car that you're going to drive on the highway. So of course it's off-road. I mean, this is a tiny little RC racing motor. So if it's on the road, it's probably going to get crushed by some truck. So there it is, brushless DC motors, and that's a good thing to know about, I think. If we take a look at some of the homework questions, this is the preview for homework 8 on steppers, which is due this Thursday. You can see that what we've gotten here, the ULN 2003A, which is what we used in the lab, is a little more than an array of Darlington transistors conveniently housed into a dual inline package, a DIP or integrated circuit. And in fact, if we scroll on back, you can see sort of the schematic diagram of the ULN 2003. And it's really just a bunch of drivers. It's not really doing anything, except it's decoupling the common from the ground, and it's giving you your own power. So you can put in power the way you like. And all of this came about in 1953 by this gentleman who came from AT&T Bell Labs. And that is Darlington. And he had his little patent, which we can read about if we like. And he just called it a semiconductor signal translating device. So that's Sidney Darlington. And he's the inventor, named as the sole inventor, but his patent became assigned to Bell Labs, as happens when you are a Bell Labs employee. And I don't think he's around anymore. But anyways, we could probably look him up if we needed to. So I was just wondering if you had any questions about homework 8. I'm just going to sort of scroll through these things. The ULN 2003 we've already used. Yes, they can sink 500 mA of current up to 50 volts. Your little Arduinos can't do that, right? Little Arduinos are good for, I think I was just doing an experiment with 3.3 volts. Anything after about 50 milliamps off the 3.3 volt supply basically is unreliable. And even 50 milliamps is pushing it because the little regulators on there are, well, not up to snuff. And that's just the regulator. If you're trying to draw directly from the little 8-bit toaster controller that is the 328P, you'll be sorely disappointed after 30 milliamps. It just won't do it. Let's see now. You can stack these one on top of another. right? So this is interesting, right? So if you take these two dual inline packages and you just stack them and solder them up, in fact, you can get an ampere out of it, which is kind of neat. I haven't tried that myself. And if you're going to draw an ampere out of a piece of electronics like this, you might want to consider throwing on a heat sink. But they say you can do it. So I'm going to believe them on that one. You're basically creating a high current output, which you may need for, I don't know, something that is a beefier stepper motor than what we've been using. Although we could drive beefier ones with what we've got in terms of the ULN 2003, as long as we've got enough power. So let's see now. What else do we need to know? Okay, so here's question 18. And what is the question? You really need a microcontroller to generate a sequence for unipolar steppers. Does that seem true? I mean, look at this sequence. What does it remind you of? All right, 1100. Well, these are this is the complement of that. So it's going 3, 1, 1, 0, 0, 0, 2, 2, and then repeats. That sort of feels like a finite state machine, doesn't it? Do we really need a microcontroller to generate a finite state machine output? You guys took Digital Design 1. You tell me.
No.
No, not no, but heck no, because we've taken Digital Design 1 and we know how to make a sequence of numbers like this without a problem. And in fact, if you get your little ESC controllers, it's probably not going to have a little microcontroller in it. Although it could, I don't know. So then here it says, and I by the way, I've designed these for stepper motors just using normal TTL, the 7400 series MSI TTL. It's not that hard. Make a counter, you decode it, there you're done. So here's a half-stepping sequence. To half-step a stepper motor, use the table on the right as opposed to the table on the left. Half-stepping is supposed to give you greater precision. And you can kind of see these don't look identical, right? They're close, but not quite the same. And so, yeah, you've got a different sequence you can use to get higher precision during your turning. And then it says you could build this with 4 JK flip-flops and a 555 timer. Well, now let's see. How many states is it? 16? 16 steps. Actually, yeah, 16, 0. 1 through 16 is 2 to the 4. So, because it didn't start at 0. If you start at 0 through 15, that would be 16 steps. Starting at 1 and going to 16 is also 16 steps. So, looks like 4 JK flip-flops. That sounds good. A 555 timer will probably give you the clock pulse on input. You might need some extra logic, right? But it doesn't say you can't have it. It says you could use, you can build it with this and that. It doesn't say, and you need extra stuff or you can't use extra stuff. So what do you think? Does that sound true? A little extra logic. Can you build a finite state machine that has 16 states? You're Digital Design 1 gurus by now. You should know the answer to that. So I'll leave it to you. Modern RC servo position is not defined by the PWM duty cycle, i.e. on-off time, but only by the width of the pulse. The width of the pulse. Is that true? If you ever have questions about stuff like this, you can look it up. You could look up PWM and servos if you like. and look at servo control. And you could see how this is working, right? So you can see that pulse width modulation is being used. He's changing the width of the pulse, but he's not changing the total duty cycle. Although one could make a compelling argument that these two things are sort of similar. But he's doing a, as he says, pulse period modulation. So that's a true statement. Let's take a look at some others. I mean, you got any questions about this? I mean, you guys are quiet, so I can't tell. Are you thinking? I can't tell what you're doing. Is this the pained look? Giving me the pained look? I also wanted to show you something about this this lab that we're going to be doing this coming Wednesday. I've got an interesting lab planned for us, and I wanted to cover that as well. And that's going to be coming up in the area of I2C buses and real-time control modules. So I thought you might find that interesting, and I think we should probably cover that. So you tell me now, is this true or false here? We're trying to do question 20. This is your homework for this coming Thursday. Any ideas? I'll just proceed through it if you think you know the answer. Any questions about question 21? Or question 22? It looks like it should stay in position, that should say. Let's see. That's a small typo. Position. Looks like 3 people have already tried this question. This is question 22. Somebody must think they know the answer if they tried the question. And then question 23. Now here's something that's interesting looking. There's this little control circuit. Here's my motor, and there's a potentiometer. That's my feedback. And now here's the output spline, but somewhere in here it's geared toward this little potentiometer so that we can have feedback for the servo. So this is a pot, that's a potentiometer in the servo. Does that provide feedback to the controller? Does that give us the shaft angle for this rather inexpensive looking DC motor? This, by the way, is considered, you know, the more expensive type servo, but you can see it still has the silly plastic gears in it. You can get them with metal gears. It's a little more expensive. So what do you think? What's that pot doing there?
Is it true?
You're not sure. It's giving us feedback. It's telling us the position angle of the shaft, so that when you go to set the position of your servo, this potentiometer will make sure that it's at the correct position by giving feedback to this little controller chip in there. So if you wanted to, you could build your own servo controller. You can build it out of a little 555 timer, and that's going to give you the ability to change the width of the pulse. This is the design for the servo controller. And basically, you don't need an Arduino. And this little 10 kilo ohm pot will change the pulse duration, and that'll give the servo the ability to be positioned by the 555. So you can turn this knob and get the servo to turn remotely, which might be good if the servo is hooked to an antenna and you're trying to steer the antenna. Or if it's hooked to, I don't know, something else. Maybe the little jet that comes out of your jet boat, or whatever it is you guys are doing for your for your little project there. So here comes a sine wave generator, and we've done something with that. Do you think you could write a Java program that outputs samples for the sine wave with 12 bits of precision and 512 samples? And so this is the 4921 SPI interface DAC on the 8-bit analog digital converter mode. And so let's see, somewhere in here, oh, there's a sine table. But this sine table, this doesn't look very good, right? Because this is an 8-bit sine table. So we can see a list of hexadecimal numbers that have been pre-computed and are being stored here in this little sine table. What if I wanted to go to something like he's asking here? He's saying, but what if I want 12-bit output? And for that, well, we know that sine is a trig function that varies from -1 to +1. If we add 1 to it, it varies from 0 to 2. If we multiply by 2048, it varies from 0 to 4096. And if we use that to populate the sine table, then essentially we have nice scaled 12-bit numbers. So we can change how these things are working. You can see it's being done here with fill sine wave. Right? And so what this is doing is it's allocating whatever the size is of the DD array, which I assume to be 512. Yep, there it is. It's turning it into 16-bit unsigned ints, and it's filling it up with the, this is my increment on theta. It's filling it up with a computed trigonometric function that gets assigned to FD, where FD is probably, yep, it's a float. FD is a float. And so then we take the float, add 247 to it, and this is going to go minus 247 to plus 247. So then we add 247 to it, and then it goes from 0 to 4095. That's what I think it's going to do. And so 4094 maybe. And so then you put that into your DD array, and this gets truncated. The floating point part gets lopped off. C doesn't care when you do things like that. Java wouldn't like it. You'd have to cast it, but C is okay with it because C is like built for wild and crazy times. So that'll do that for you, and the rest is like DAC write stuff where the output buffer gets sent to the SPI interface. And let's see what else we need to know about this. Is there like a question in here? Oh, it's true or false. So it's sounding an awful lot like the answer to that one is true. What do you think? Is that all right? Enough coverage of homework 8? Any questions about homework 8? I think we got through most of it, yes, last time. But I'm happy enough to answer any questions if you have any. So there's homework 8 in a nutshell. I think you guys are ready for it. And I know some of you have already taken it. Let's see. So we had our steppers. We saw our little video. I'm going to call this stepper thing a done deal. That's the end of homework 8. You guys can submit that on Thursday. Let's talk a little bit about this other thing I've got going, which is the let's get rid of this one. Get rid of too many windows. There. So what I wanted to do, so let's switch courses and go over to the embedded microcontroller lab. Look at the course content and take a look at what's going to happen this Wednesday, because I think it's educational if we can get a lecture that kind of relates to what we're going to see in the lab. So I guess we're up to lab 10. How about that one? So lab 10 involves the so-called real-time clock and the I2C bus. And let's start by taking a look at some of the hardware. So this is a data sheet for a Dallas Semiconductor 1307. Now, Dallas Semiconductor took over Maxim Semiconductor, so oftentimes you see a Dallas Semiconductor chip with a DS in front of it. Sometimes it says MAX in front of it. But they're both the same company now. And you see why it says MAX, because it's Maxim integrated. And Maxim was well known for creating exotic mixed signal integrated circuits. That was their forte. In case you're wondering, mixed signal means a combination of analog and digital in the same package. So they'd make an RS-232 to TTL level converter, which would essentially take 0 to 5 volts and convert it to plus minus 10 volts using a little internal charge pump and put the whole thing on a chip. Stuff like that. Really useful, kind of expensive little chips that you could integrate into your project and would help jumpstart things. So what we've got here is interesting. We've already built our own clock, but this one's different. This one is going to give us the ability to keep the time even if the power to our Arduino is turned off. And so that's kind of neat. It uses very little power. Look at this, 500 nanoamperes in battery backup mode. So what's going on here is you take a little quartz crystal and you add it to the chip. That's kind of an unfortunate thing you have to do because it means you have to add stuff. And when you add that crystal, what you're adding is something that vibrates at a frequency of 32,768 hertz, which happens to be the same frequency that you would find in a common quartz watch. So basically, you're putting in a chip with a quartz watch accuracy. And if you wanted to, you could externally synchronize this chip, perhaps next time it gets plugged into a GPS system or a radio that can receive CHU Canada, which is a atomic clock that's being broadcast from Canada. Or if it has access to the web or the net, it could go out to get network time protocol. And in that case, it can synchronize itself to an atomic clock every now and then. And if you look at how atomic clocks work, and this is kind of interesting, actually, they have a little crystal control clock too. And they synchronize that crystal control clock to the vibration of cesium atoms. And that allows the clock to kind of run in a dual mode. In its free running mode, when it can drift perhaps 1 second per month or something like this, versus its fused sensor mode, where it makes reference back to the cesium clock. So what you can do here is get this to run in the similar fashion so that it basically free runs most of the time, and then occasionally when it's able to, it synchronizes with a satellite or maybe broadcast station or perhaps the network. And in those cases, when the CPU wakes up, it should be able to get a reasonable notion of what time it is, including the year. And it says here, well, I always try to research these things. How accurate is it and for what period of time? And he says it's compensation valid up to the year 2100. I don't know how to test that. Maybe that's true. How would I know? I'm not going to live to see it. So it comes in different packages. And when you go to buy these things for your design, you'll probably want to start with something that you can easily solder. So a parallel dual inline package with 8 pins looks just like a 555 timer. And you can solder to that with relative ease. You can even put it into a socket. And when you get to the lab, that's the kind of chip we'll be using. But if you want to do automated assembly, you can get the small outline version of the package, and that enables you to put it onto a so-called tape, and that gives you the ability to use a pick and place machine, and it'll chug it out like chiclets with a machine gun. Do machine guns chug out chiclets? Well, it'll shoot out a whole bunch of these things onto your boards as they go by. Presumably, little boards are panelized into big boards, and then they get assembled all at once, and you run them through the oven. So that's an interesting little chip. It has a few features aside from the fact that it only takes a few nanoamperes. Not the least of which is you'll find mine have, well, the ones we're supplying in the lab come with a little battery. The lithium batteries on those have been wearing down, so you may find there's an error coming in, and if that's the case, we'll bring in some more batteries just so you don't have a problem. Usually they're good to within like 10 years, but for some reason these are failing quickly. Don't know why. There's another thing going on here with this device. It's not using SPI. It's using a 2-wire interface, and that is a little bit unusual for us. So here's SCL, that's a serial clock. Here's SDA, that's serial data, and notice it's bidirectional. So this is our first encounter with the I2C interface. I2C interface is a really nice interface in terms of its simplicity. It doesn't use a chip select. Instead, it uses addresses, which means that devices have to have unique addresses when they sit on the SDA bus. The serial clock for the bus can't exceed the rate for any given chip that sits on the bus. And in fact, you don't want to just match the rate, because if you do that, you're really not giving yourself enough margin for error, especially if there's a little clock skew when you start to distribute the clock pulse. This X1, X2, that's where you hook your external crystal. And you can see there's a little tank oscillator with an inverter, and that's just set up to keep things vibrating in the crystal. And then he's saying, well, you can have a 1 hertz crystal or a 4096, that's integral power of 2 crystal, or 8192 hertz crystal, or a 32,768 hertz crystal. And that 32 kilohertz crystal, that's common. That's the one that's the cheapest. And you'll be able to find these, these modules are relatively inexpensive. The component parts, oddly enough, are a little bit more. Then there's this this battery backed up RAM. And that is going to store the initial date and time and year and day and whatever. And that'll give you the ability to reset the clock that's internally being kept here. So what's interesting about this device is not just the fact that it's able to give you the time, but that you're able to control it with an I2C bus. So that in and of itself makes it a useful thing to look at. And I think it's important for us to consider that if we're in the course that allows us to interface everything to everything, well, we have to recognize that there's more than one kind of bus. SPI bus, which is high speed, and maybe has a few extra wires, or I2C bus, which is lower speed, but has fewer wires. And so that's kind of neat. It's also a bidirectional bus, and it uses addresses, so that's cool. And then over in here, we see a little field effect transistor coming out of this buffer, which enables us to get a square wave on output in case we need that for something or other, like maybe a squared up version of the I2C. Well, a squared up version of this little clock could be supplied to an interrupt, I suppose. And the rest of this is more specs, so I don't think we need to do much more coverage here. The battery backup. This is the 3-volt lithium cell, and it's typical for these things to last 10 years, but I don't know why. I just heard that one of them was reporting that the battery voltage was low for whatever reason. Let's see now. What else do we need to see in here? It's kind of an interesting thing to tour the data sheet. Here we go. So now if you want to do, this is like theory of operation stuff. If you want to do stuff where you're actually able to write to the registers, it's really good to know which bits do what. And for you to know that, you would have to read the directions. You have to read the directions. And so here are the timekeeping registers. And so that gives us some insight into how to write a driver for this chip. But thankfully, we have libraries which enable us to use the module without writing our own driver. And that's really important. And that's good. I mean, you want that. You want software already written to support your hardware, if at all possible. Otherwise, you're going to end up writing your own device driver, which in and of itself is not a particularly attractive proposition unless you're planning on bringing a new chip to market, in which case writing a device driver is a perfectly legitimate thing to do. There's some more control register stuff, but as I said, we already have nice drivers for this, so that's convenient. And so let's see what else we need to know. Timing diagrams I'm not going to get into now. I think that basically covers everything we need to know here. Let's take a look at how we can get some drivers for the Arduino. So here under Sketch, and this is not built in, so you're going to have to do this, all right? You got to go to the Include Library and then go into Manage Libraries. And then you're going to get a dialog box. And what you're going to do is constrain yourself to timing. And I'm just going to look at the stuff that's already installed. And now you can see that I've got the DS1307 little real-time controller library. Here's one for a different chip we're not using, so don't install that, although I did. And in fact, if you see something that you don't want, you can uninstall it, I suppose, but I'll leave it. And here's one that I've been using. This is called the 1307 real-time clock timer library. And so that's installed. I got version 1.6.0. I can select an older version. I'm not going to because I don't want that. Once you do the install on something like this, let's see if we can find something that's not installed. Oh, well, this is already saying it's installed. So let's say all, or even better, updatable. Nothing's updatable. All right, so we'll do all. And just check it out. Oh, here's one for network time protocol. So if I wanted something like that, I could hit install. And there you go. It's installed. See, it says installed. So that's cool. That's how you get your libraries, or at least it's one way to get your libraries. When you go to your examples, you should be able to find, sometimes they say you have to reboot the Arduino IDE, but I haven't found that to be the case. So here's the RTC, the real-time clock by Makuna, and there's the 1307, simple. And what you want to do is go to the simple, and there you go. He shows you how to wire it up. And that gives you a little bit of insight into the code. You know, what he's doing here is he's giving you a nice wrapper around all those wonderful registers that we saw defined before. And so what I did was I kind of put this together and ran a little video, made a little video for you, which I'm planning to play even as we speak. So if I go to courseware microprocessors, I should be able to find a real-time clock video. And that's convenient, right? Because we did the LCD clock, but it didn't have a real-time clock associated with it. So what I'm looking for here is not jumping out at me. I thought I did this one already. Let's just do a quick look. Find RTC. Not here. Real, not here. Clock. Enter. I thought we did this. Didn't I do this already? Jeez. I'm having a senior moment. So let's see if it's in here. Nope. All right. Well, life in the big city. I'll upload that later. This is what we can use. Here's a Word document, and the Word document basically is my notes on how to put these things together. So this is what you're going to get: a little module with a 32 kilohertz crystal, the DS1302 built into the module, the 2032 3-volt lithium battery. And in case you're wondering, what does this 2032 mean? Does anybody know? You guys probably have to buy these batteries for whatever. Well, 20 refers to the diameter in millimeters. So this is a 20 millimeter diameter coin cell. 3.2 is also the diameter in millimeters divided by 10. So it's a 3.2 millimeters. So this is 20 across and 3.2 millimeters thick. So that, in case you were wondering. Lithium batteries is supposed to be good for 10 years. Let's see now. Here's the serial clock. There's the serial data. There's a reset line involved. Ground and VCC. And that's it. And this is a picture of what comes out of the data sheet over at Dallas Semiconductor. And there's that block diagram, which we saw from before on the data sheet. So that's cool. And let's see, here's some stuff about it. Here's how you get your library. So you might like to, I don't know, print this out or take a look at it if you're going to set yourself up in the lab this coming Wednesday, because you're going to have to do all this. And you're going to try the DS1302 Simple, which is, just a screen capture of what I was showing you from before. And here's your data sheet. Now, here's a cool idea. We're not doing that, okay, but it's a nice idea. You can use Canaduino. How about that one, Canaduino? Canaduino for 1363 comes with a big antenna. That's a AM antenna. And what that's going to do is it's going to pick up CHU Canada. And so what it'll do is not only will it include, and you can sort of see it here off to the left, a 32 kilohertz crystal with some sort of a Dallas Semiconductor 1302 equivalent, but it'll also be able to resynchronize from the atomic clock that you can receive on the AM receiver. So that's cool. For $13, you get like atomic clock accuracy if you need it. And that's actually cheaper than a GPS module, which could do the same thing. But if you don't need a GPS on your project, this might be a much nicer alternative. And so that's that. Let's see if we have anything else I can show you about that. I just wanted to see if we can find the original document here. And this is working ahead at on my next lab here, which is called the NRF24001. So here's what we got. And here's a little extra code, which I threw in. But in fact, you're going to get that from the simple example. And now here's a memory test program, which you can get from examples. It says Marcula, isn't it? There it is, Mancuna. Memory test. So that'll give you the memory test example. So it lets you write and read from the memory inside of the 1307 chip. I have to keep looking at it because I keep forgetting. And then what else do we need to know about this? I'll just go back to the notes on the Word document here just to make sure. So this is a printout of that code which we got right off the example. And here's what you would expect to find when you're running the "Hey kids, what time is it?" program. And it goes in and queries the real-time clock. So that's fun. I think you guys will have a good time with that one. And I can sort of see why you wouldn't necessarily create a video of this thing printing, because what's the point? You guys are going to do that yourselves. And let's see, what else do we need to know? I guess that's it. The connections, these are Arduino Uno connections. And you'll see that here, right? I mean, if you go to the top, you'll see what he's asking for right in through here for the memory. And if you go to the Arduino Simple, you see it again here. But if you wanted to take a look at the actual connections that I'm using, you can see it says 452 for data, clock, and reset. And so that's the 3-wire interface, data, clock, and reset. Let's see if he's got that in here anywheres. Was that in the memory example? Well, for some reason, I'm not seeing it right away. So this is memory test for 1302. Which one is this? 1307? Let's bring up the memory test for 1302. So that would be, I got too many things installed in here. RTC, 1302 memory. Let's see if he's got it. Yep, there it is. So that's that should work the same as the other one. And you can put that in if you like. So that's cool. Let's see what else we need to know. I think that's it. That covers it. And it's a it's kind of a cool little module. You can see the DS1307s. Oh, this says 1302, doesn't it? But it says 1307. I'm not sure what the difference is between a 1302 and a 1307. DS1302 versus DS1307. The DS1302 will charge the battery, the DS1307 won't. 1307 has more RAM, programmable square wave output. I don't really want to charge this battery because it's not a rechargeable battery, so I think you're better off with the 1302, but the code will probably look the same if you wanted to use the 1302 code. That's cool, actually. And I didn't realize that. So DS1302, or DS1307, and we should be able to see a picture. Yeah, here's one. So that's a 1307. This one's got the small outline instead of the dip, but the pin functions are the same. They don't show you one with the dip. This picture is only showing the small outline. Let's look at the 1302, see if we can tell the difference by looking. Oh, here it is at 43 cents. That's cheap enough, isn't it? So, yeah, there's the Dallas Semiconductor 1302. This here is going to be your crystal. That's the CR2032 battery holder. And these are your hookups. So you'll use 4 DuPont cables for that. And what else do you need? This is pretty much all you're going to get when you come into the lab. That plus the DuPont cables and an Uno, that ought to get you set up for your first I2C experience. So that's kind of nice, and you'll have a nice lab out of that one. And let's see. You'll be using the 13. Oh, it's a 1301 chip. Detailed hookups. I have a feeling the 1301 has a nice example as well. Let's see. I'm going to just find this again. It should say RTC 1301. Yeah, see, I don't even see a 1301 here. Odd, isn't it? Just out of curiosity, it seems as though I've got a variety of different clock modules, some 1307, some 1301, some 1302. I don't think it makes a difference. So that's a little preview of the lab. And let's get rid of some of this mail here. And that's that. Any questions about this lab coming up? I had a 1307 data sheet. I'm convinced that's what it was, but just bear with me a minute. All right, I'm back. Yeah, it's a 1302. I don't know why I wrote 1301 and 1307, but this is a 1302. That's what it says on the module. I wonder if there aren't some that are a little bit different, because this one doesn't look quite like some of the others that I've seen in the lab. So there may be a little bit of variety. I'll try and get it so that we're consistent, because now that I look at this, I realize that there are small variations in the modules between what we've got in the lab and what I've been using, but it shouldn't matter too much. I've got mine all wired up already. And I've just hooked it up to my little Arduino. So my little, how do you say? Yeah, Arduino. So that's plugged in. Should be able to upload it. And I'm uploading the 1302 because, well, because that's what I have. And if I go to the serial monitor and set it to 57600, here we go. It's giving us the time. I think it, yeah, it's storing a little data out into its little RAM brain, which is battery backed up. And that seems to be working. So that's the example from 1302 memory. There's another example I saw for 1302. Let's take a look. Should be able to run that as well. This is under real-time control, RTC. And let's take a quick look. 1302 simple. And let's see if that works. So I didn't record the video on that. I don't know, giving you a live demo, but certainly easy enough to get these things working. And here you can see compile time is newer than RTC time because he's stored in RTC time already. So he says that's expected. So he leaves the time alone. If it wasn't newer, then maybe it wouldn't update it, I'm guessing. So that's a quick demo of the 3-wire interface. And what do you think of that? Cool, right? It has the look and feel of, I don't know, something that you guys will have a good time with. You'll come in, you'll try that, and it'll hopefully work without issue, as it has for me. You'll have to wire it up, just as I've done here, and that's it. And you'll be done. You'll have your code. And you'll maybe take a picture of it, wired, I suppose, and then throw that into a Word document and hit submit, and that's your lab. Any questions about this lab coming up this Wednesday? All right, then. So we've covered the lab for this Wednesday. We've covered the homework for Thursday. Let's move on to bigger and better things. One of the things that we've been sort of skirting around on the details for is serial ports. And I really did want to get into it because the I2C interface is really a serial interface. And as a result, we're going to need to know how to do serial communications for a couple of reasons. First, I2C is serial, and so we're doing a serial interface. Second, if we want to type into the Arduino and have it read our instructions and then type back to us, that's using a serial interface. And third, my plan is to use the NRF24L01 radios in order to be able to do serial data communications. So we're going to have a nice RF lab, that is a radio frequency lab at 2.4 gigahertz using the ISM, or Instrument Scientific band, which it's kind of halfway up on your microwave oven's dial or something like this. It's a it's kind of an interesting thing. It's unlicensed. You can have your own little radio. You can broadcast to all the other little radios. And in fact, that's great fun. You know, you can have everyone in the class have a receiver and they can all receive the transmitted contents at the same time. And it doesn't clog up the airwaves any more than just sending one thing to one person. So that, you know, broadcast is really a very efficient way to distribute data to many microcontrollers. There's also a possibility to do encryption and to do all kinds of other things. There's a little bit of a thing here about serial ports, and I think it makes sense for us to start to look into them a little bit. So first thing you want to do, take a look at this load cell video. A load cell is a means of measuring deflection for materials that are being moved in their elastic region. That is, if you bend them to the point where they don't bend back to their original shape, which is known as plastic deformation, you've essentially broken the load cell. You don't want to bend load cells beyond their original shape. Here's a nice example. And what I'll do is I'll hold the headphones up to the microphone. Hold on. The load cell to the standard IACT20201103 board. We're using a standard clock going into pins 2 and 3, and then we have to wire up power to the IACT711. Since we're doing pins 2 and 3, we have to make a small modification. Here we're using 2 and 3
data out and the serial clock. And so that's what happens when you use the scale begin. Otherwise, what you can do when you want to find the code is you go to File, Examples, and then you're looking for the HX711 master, and this is the standard code. Normally, when you start something like this, it comes out with pins A1 and A0, but I've already reserved those for the serial for the Arduino Audio Shield. So that's why I switched to 2 and 3, so I wouldn't be occupying 0 and 1. When you look at the output of the system over in here, you can kind of see the average, and as I manipulate the load cell, you'll see that it's changing the weight, and I'm pushing it to 19 grams worth of force on the load cell. And so that's my little load cell demo. Hope you liked it. Thank you. Boy.
So that's the load cell. I don't know. Were you able to hear the audio okay? Was it too low? I was worried a little bit about that. But anyways, I've got this idea that you guys may not have seen load cells before. And if you haven't, this is a good thing to be looking at. The load cell uses a very high dynamic range analog to digital converter. The 24-bit ADC is very slow, but what it's doing is known as a delta sigma analog to digital converter. So it's essentially working in a way which is completely different than the so-called successive approximation ADD converters. And that in and of itself is another whole lecture, which we can do later. If you wanted to, you can go and you could say, gee, I wonder if I can find a data sheet for the HX711. And the answer is yes, you can. And they're not terribly expensive. And you can get these on eBay. And you type in something like data sheet. It should come right up. And there it is. So this has got a programmable gain amplifier. It's got, this is called sometimes they say delta sigma, sometimes they say sigma delta. You can see it says sigma delta in Greek. And that uses a comparator and an integrator and a little bit of feedback and creates a 1-bit ADD converter. And it essentially gives you the ability to sample relatively slow rates with slow rates of change with very high precision. So this is a great kind of ADD converter to use if you don't plan on sampling very often. And the sample rate on something like this, he's saying, is like 10 samples per second, 80 samples per second. Or if you know that you're going that slow, it's relatively easy to build a high precision ADD converter. And that's perfect for doing something that you're just measuring the weight on. This also has an interesting interface going through the analog inputs and of the Arduino. And so that's a feature that requires that you have reasonably good signal and precision. Let's see now. What else do we need to know? I think that's about it. So you're going to end up, these little guys over in here are your analog inputs, and they're going to be hooked to the strain gauges, which will be mounted to load cells. Now the question is, did they give us a nice picture of the load cell? They gave us some sample assembler code, but I don't think reading the assembler is going to be very educational for you guys because you don't know assembler. And I think we saw a load cell. Let's see one hooked to a HX711, just for yaks. We should see some pictures of that. So here's your basic load cell. It's just a bar that's been drilled and had some strain gauges mounted to it. I have one of these. This has got an integrated platen for the top and the bottom. And here's the HX711 in a small outline integrated circuit. And you can see these very fine wires which are hooked up to the load cell. And then you get a nice I2C output here. So that's cool. Let's see. Yeah, 4 wires. It's probably ground, 5 volts, serial clock, and serial data. And that's sufficient. So he's doing an awful lot of work for you. And basically, you can use this to measure, well, for this load cell, weights up to 5 kilograms, which means it's like a postal scale. But you can get these for much higher weights. So let's see, 24-bit ADD converter. Look at the data sheet. That sounds good. Oh, here's a picture of a load cell. And you can see they've drilled it out to make it so that when its deflection is made at the end and it's fixed at the other end, presumably as long as you stay within the 36 kilogram rating for the cell, it doesn't have plastic deformation. In other words, don't step on it. Right? You can make it to measure a number of different kinds of loads, from small letters. This would be like a postage stamp. Well, U.S. postal mail, to train cars, and that is true. You can make these things any size you like. Double-ended shear beam, a straight block of material fixed at both ends and loaded at the center. What's the question? What's a load cell, I guess? That question looks like it's got a bug in it. We should find a way to fix that. Geez, that's not right. I'll fix that later. Let's just make a note. Question 3. And that's in homework 9. Here's a picture of a strain gauge, and you can see it's just a long wire that's running back and forth. And then when you proceed to stretch it, it changes resistance. And what you want to do is try and measure that change in resistance. And it says it's more sensitive in the horizontal direction than in the vertical direction. The horizontal direction would be this way. Vertical direction would be that way. So what do you think about that? Which way would it be more sensitive? Any ideas? And take a guess. So the answer on this one is true. It is more sensitive in the horizontal direction than in the vertical direction. You're pulling at the little joints in all of these little corners in here, and it changes the resistance more rapidly. Electricity, oddly enough, doesn't like to go around sharp corners. And when you're designing a printed circuit board, you want to avoid sharp corners in your printed circuit board traces, because each one is going to work like a little radiator, like a tiny antenna. So if you're designing antennas, the sharp corners might be good if you're doing a microstrip antenna. But if what you're trying to do is design a circuit board where the electricity flows smoothly like water, you don't really want to have sharp corners. Oddly enough, currents don't like going around corners. So let's look at some of these other things here. Invented by Edward Simmons and Arthur Rouge in 1938, the most common type of strain gauge consists of an insulating, flexible backing which supports a metallic foil. The gauge is attached to the object by a suitable adhesive such as cyanoacrylate. What's cyanoacrylate? Anybody know the common name for that? It's super glue. It says it right here. So that is true. And here's another picture of a load cell. They're exquisitely small. You can make these things absolutely tiny. You put them on flexible membranes and you can stick them on stuff like buildings or on structures that people might have to cross, like bridges. So here's a famous name, Wheatstone. In 1843, he devised the so-called Wheatstone Bridge, and we use a Wheatstone Bridge, which is going to compare resistances between one another in order to be able to figure out when a strain gauge is, well, being strained. And here's an example of the Wheatstone Bridge. So what we'll do is we'll have a calibration resistor, which is tuned, an unknown resistance in here, and two known resistances. And we'll adjust these so that the gauge, the voltmeter in here, is registering 0. And then when this is under compression, it goes one way. If it's under expansion, it goes the other way. It's the opposite of compression, I guess. And so that's essentially what you're trying to do when you're creating a load cell. The strain gauges are dotted at orthogonal points with respect to one another in the cell. And then you can measure deflection in this way. In fact, all you need is a voltmeter and a battery, and you could hook it right to those load cells. You don't actually need an HX711 chip or even a microcontroller. You can do the whole thing with a galvanometer. How am I doing on time here? I think we are getting close to the end. Let's try one more question. So this is cool. Right now we're seeing sort of the schematic diagram of the load cell with a strain gauge here and here. This one's under tension. This one's under compression. That one's under compression. This one's under tension. And there's some load coming in from the right. The left-hand side is fixed to some sort of fixed frame of reference. That might be like the scale housing. And this might be the scale platen that has some flexure, goes up and down. And so now I've got my little strain gauges mounted to the beam. And the entire assembly, beam plus strain gauges, is called a load cell. So that's what people mean when they say they're using a load cell. And that's your Wheatstone bridge right in there. And you can see compression, which you would get here, tension, which you would get there, and then another set for tension and compression. So that would be tension, and then this would be compression. And so then you'd be able to look at the voltage out, that's where V is, versus the voltage in, that's this battery going through all of these things. And that should give you a chance to figure out just how much compression or tension your beam is on. And yes, doesn't it indeed look just like a Wheatstone bridge? And that's the key, right? You have to measure exquisitely small differences in resistance and come up with a voltage that's somehow proportional to the deflection of the member. And so that's how load cells work. That's kind of important for mechanical engineers. They're measuring loads on structures like bridges because they want to see if there's too much deflection. If there is, they may be close to a failure mode. And I think that's all the time we have for today. Thank you very much for your attention. I hope you found this educational. We'll get to the serial ports and a little bit more about load cells in our next exciting microcontrollers lecture. Thank you.
Thank you.